I have Helvi Witek here to talk about numerical relativity for black hole microstates.
Thank you so much, Nick and Joseph. And I think I just got the sign from the back, so let me take this off, making sure that this is working. Wonderful. So yes, a big thank you to Nick and Joseph for inviting me here today to talk about numerical relativity and its possible applications to microstate geometries. There is a question mark on purpose because we don't know how to do this yet, but I want to convince you that we actually know the different puzzle pieces that we would need to do numerical simulations of microstate geometries. Now, the other reason why I'm so delighted to talk to you today is that for me, doing numerical relativity simulations really is one pathway to connect these theoretical ideas, theoretical models of how we could represent black holes to actual observations. And in the background here, very faint, you can actually see the gravitational wave signal measured in 2015 for the very first detected binary black hole merger. So if we talk about numerical relativity, I really want to ask the question, well, why do I think numerical relativity for microstates is interesting? And I also want to give a disclaimer of what I mean by that. So I know there is a lot of excellent work already going on in looking for solutions, using numerical methods by now to look for solutions of microstate geometries. When I talk about numerical relativity, I usually think about solving a time evolution problem, dynamical problem, and the standard application, of course, is general relativity, but I also want to think about with you on how to extend this. And we typically think about this dynamical problem in 3+1 dimensions, which means we typically solve this on high-performance computing facilities. So that's what I mean by numerical relativity. And where I think this can be interesting for microstate geometries is to think about out of equilibrium dynamics, can I find new solutions? Can I think about linear and nonlinear stability or instability, and what is my new equilibrium state? And if we are very fancy, we might even think about how we might connect these microstates to gravitational wave observations. Now, the funny thing is, before I came here on Friday, I was meeting up with a friend of mine who is a computational biophysicist and fellow actor, and he actually said, well, I can't believe that there's no such thing yet as numerical string theory. So apologies, I, of course, approximated the overall topic to string theory, so I can't believe that there is no facilities yet to model dynamical systems in string theory. And I think part of the answer is that it's actually challenging, but I think we know how to do the individual pieces, and I think it's time to do this now. Okay, and I think we are ready to do this. So what do you mean by okay, so this was just so the question is, what do you mean by numerical string theory? And here we were talking about really the dynamical problem. Are there interesting questions that we can address in a time evolution problem? I know there is already a lot of really good work looking for solutions, so there is already numerical work, so I wouldn't want to claim that. Possibly. So as I said, this was a conversation with someone who is not a general relativist, not a string theorist. He does biology, and we were just chatting and brainstorming, and I was telling him that I'm coming here to share my thoughts with all of you on what is numerical relativity, what we might be able to do, and maybe we can even define this together. Okay? So what I want to do today is actually first give you a bit of an overview on where we stand in observing the gravitational universe, and we want to spend quite some time on that. I want to give you an idea of what I mean by numerical relativity in the context of general relativity. So what are the techniques? What are the problems that we need to think about? Because that's then what we need to think about if we want to extend it. And I want to advertise some work in numerical relativity beyond the standard model, beyond general relativity. And the last part is coming back to this question on how we might be able to extend the numerical relativity techniques to microstate geometries, or, as I said, open problems in string theory in general. Okay, I would also say, I know it's a kind of new topic, so please do interrupt me if you have any questions. Okay, so let's start with observing the gravitational universe, and I actually want to start with electromagnetic observations. So here what I'm showing you observations of stars close to our galactic center, taken by the Keck Observatory. And if you follow these trajectories, and this was done for more than a decade, you see that they seem to orbit around a compact, massive object. If you can even do this with Newtonian gravity, you can estimate what the mass of this object is. Turns out it's a supermassive object that has more than about 4 million times the mass of our sun, and is so compact that the current best explanation is that it's a supermassive black hole. And actually this discovery was so important that it gave half the Nobel Prize in Physics in 2020 to Andrea Ghez and Reinhard Genzel, the other half going to Roger Penrose. Now, staying with electromagnetic observations, we of course also have black hole shadows, and I'm sorry for the lag here. You've seen this in Daniel's talk, and I believe we will see this again in Alejandro's talk, so I'm not going into much details here, but this is an image of the black hole shadow of Sagittarius A star, so the black hole at the center of our Milky Way, taken by the Event Horizon Telescope collaboration. Now, what I want to focus on mostly is actually observations in gravitational waves. So if we have two compact objects, two black holes orbiting around each other, they will distort space and generate gravitational waves. What I'm showing you here, and I realize it's actually quite dark on the big screen, is a simulation by my postdoc Deborah Ferguson, where you have the black holes here. I will start the simulation in a moment. This is a simulation of one of the most massive binary black hole mergers that we have detected so far, where our black holes have initially a mass of 85 and 66 solar masses merging into a new black hole of 142 solar masses. So this is where we go into a regime that we call intermediate mass ratios. So let me start the animation. You will see our two black holes orbiting here around each other. Thank you so much. I will also play it again. And as our black holes orbit around each other, they generate these gravitational waves. Before they merge, let me just maybe play this again. Okay. They generate a wave that's increasing in frequency and amplitude, so that's the in spiral. And as they get closer, they merge. They have a peak in the gravitational wave signal here. And then the final object in this case is a black hole that rings down, and the ring down is a exponentially decaying sinusoid with a characteristic frequency and amplitude. Now, as I said, this was just one example. If we look at the landscape of gravitational wave detections that we have so far, I want to remind you that the very first detection was in 2015, almost 10 years ago. So when I prepared the slides, I thought, wow, there's a celebration coming up next year. I can't believe it's been that long. Yeah, but the first gravitational wave detection was back in 2015. What I'm showing you here is are all the reported gravitational wave measurements from 2015 up to 2021. And what you have here are the masses of these black holes or these compact objects, and this is our timeline up to the first 3 observation runs of LIGO. These are about 90 events. In blue are our black holes. Here in orange are actually neutron stars and neutron-star collisions that we have also detected. Since then, so as I said, these were the first 3 observation runs. Since then, we have started our 4th observation run of LIGO, and you can actually check out the status of their observations on this website. If you can't see it, I'm happy to share my slides later on if you have a website, if you want to check this out. And as of last night, there are 105 new significant events since the 4th observation run restarted earlier this year. Yeah, so this is just to show you that since the beginning of the first gravitational wave detections, we already have hundreds of events of compact object collisions that we can work with, and where we have measured the gravitational wave signals that give us information about the strong gravity regime. And by strong gravity, I really mean the dynamical, non-linear regime of gravity that unfolds in the merger of compact objects. Okay. Sorry, which one? Oh, so these arrows here is just the merger. So we have 2 objects here, for example, 2 neutron stars in orange, forming a new object, and this is actually in a mass range where we don't know whether it's a neutron star or a black hole. Up here, let me see, maybe take the first one. We have 2 black holes forming a new black hole. This is all this arrow means. Yeah. Good. Okay. So this is where we stand right now. Let me also give you an idea where we stand in the overall picture of gravitational wave of the gravitational wave spectrum. So, and for this I should actually get closer here. Oh, one more thing. To highlight, the first detection, of course, also gave rise to a Nobel Prize in Physics in 2017 to Barry Barish, Ray Weiss, and Kip Thorne. In my heart, really, this goes to the entire 1,000+ people, LIGO collaboration, who made this possible. But I also want to highlight this because that means we had 2 Nobel Prizes in gravity and compact objects in the last few years, right? So this is really an exciting topic and an exciting time to be in this area and to think about how we can connect observations and theory. Okay, good. So now I come to the spectrum. What I've been telling you about so far is actually on this end here, where we have ground-based gravitational wave detectors, interferometers, looking for gravitational wave signals in the few hundred hertz to kilohertz frequency spectrum. So the sources here are stellar mass black holes, are neutron star mergers. Supernovae we haven't seen yet, but if there's one that's close enough, but not so close that it's dangerous for us, we should also be able to see this. And as I said, LIGO started its 4th observation run earlier this year in April. Now, if we go from stellar mass black holes to massive and supermassive black holes, so here I'm thinking about a mass range of 10 to the 4 to 10 to the 7, 10 to the 8 solar masses, then their coalescence will emit gravitational waves in the millihertz regime. And this includes both black holes with comparable masses as well as extreme mass ratio in spirals where you have a stellar mass object orbiting a supermassive black hole for a very long time. And that is something, so these are gravitational waves that we will be looking for with a laser interferometer space antenna, or LISA for short. And here, the fantastic news is that ESA adopted the LISA mission in January this year, which means now ESA has approved this mission. They are starting to build it, and the plan is that that LISA will be launched in the 2030s. The dates still vary a little bit, but it means that we will have space-based gravitational wave detectors to look for gravitational waves in the millihertz regime. And if we go to even more massive black holes or think about stochastic gravitational waves, we are using neutron stars themselves. And arrival times of radio pulses from rapidly rotating neutron stars to look for gravitational waves in the nanohertz regime. So this is called pulsar timing arrays, and there was a big announcement almost a year ago that they have a very strong indication for the detection of stochastic gravitational waves. Good. And then just to think about the future, I like to show this timeline. So what I've told you so far is basically up to here, 2024, where we had our first few hundred detections of gravitational waves from stellar mass black holes. The LISA mission has been adopted, and we had indication of stochastic gravitational wave background. And if we look to the future, then in the next few years, the LIGO detectors will be upgraded to their planned design sensitivity, and this is already funded. After that, there is already funding from NSF for LIGO A+, which is a more sensitive ground-based instrument, an upgrade of the current LIGO detectors. And the community is now getting together to think about really much more sensitive third-generation gravitational detectors on ground. There's an Einstein Telescope project here in Europe and the Cosmic Explorer project in the US. So this is on the ground, increasing our number of detections of gravitational waves. Then, as I said, the LISA mission has been adopted and is expected to be launched in the 2030s. So this will open the window to the millihertz gravitational wave frequency range. There are also a few plans in China to have a Chinese space-based mission in the same frequency range. So this is all to say that we have a large number of observations, and we actually will get more. So this is really the beginning. Well, it's not the beginning anymore, but it's really, an opening up of the observational window in the gravitational universe, which means we can do interesting physics, astrophysics, and fundamental physics with these observations. Good. So one thing that we do need to think about if we want to think about connecting theory and observations is how do we model this? And what I like to show for this is this image from the first gravitational wave detection, where we show the strain here. So if you don't know what that is, think of the amplitude of my gravitational wave as a function of time. And what you're seeing here is the numerical relativity simulation in red and reconstructed template overlain with this here. One thing that what I want to highlight here is that our gravitational wave detections are detections of time series signals. So if we want to interpret the sources that generate the signal, we need to model this in advance. So it's not non-trivial to invert a time series signal. So what we do instead is provide a catalog of possible signals and overlay the measurement with this catalog. Now, let me give you an example that I was thinking about when I was traveling here, and I had this girl sitting in front of me on the plane singing something, trying to remember a song. And then couldn't remember the name. She was taking out her phone with this app that actually can recognize songs. So what does this app do? It has a database of songs and does a matched filtering of what someone is singing to them, right? So trying to understand trying to do this filtering. And this is precisely what we're doing here as well, that we generate a database of songs of the universe and compare our observed data with that. Now, in order to do that, we need to construct these templates, this database, in general relativity, including both the in-spiral, the merger, and the ring down. Now, if we want to probe physics beyond the standard model, we need to include that as well. Right? So, and this is why I say in and beyond general relativity. Yeah, so this is really crucial to do. And in order to do this modeling, we actually have a combination of techniques. The one that I want to focus on here is numerical relativity, which allows us to model the dynamical regime that unfolds when we have the merger of our compact objects. Okay, So with that, I want to move to the second big part here, talking about numerical general relativity, and really just give you a flavor of how that works. But before I go there, I do want to put it in the bigger context of modeling techniques that we need if we look at the, say, compact binary problem. And what I'm showing you here really is just a schematic from our white paper for the LISA waveform working group, for which I'm a co-chair. And what we are plotting here on the y-axis is a compactness going from 0 compactness, so our objects are very far apart, to 1 is essentially the merger. And on the x-axis we have the mass ratio, 1 meaning our objects have comparable mass, 0 meaning we have extreme mass ratio, so one object having a much smaller mass than the other. So in this diagram, if we have a very low compactness, so if our objects are very far apart, the gravitational field that the other object experiences is very small, velocities are very small, so we can use a technique that's called weak field expansion or post-Newtonian theory. So post-Newtonian theory is essentially an expansion in weak gravitational fields and small velocities. And this works really well in that regime. Now, as our black holes get closer, their velocities increases, and if I say close to the speed of light, it's not really very ultra-relativistic, but even half a speed of light, which is what our black holes would have close to the merger, is something where we need numerical relativity techniques. So post-Newtonian theory breaks down eventually, and when gravitational fields as strong, velocities are order even half the speed of light, we need numerical relativity. Now, the other regimes that we have here is the small mass ratio expansion and gravitational self-force. So this is a regime where numerical relativity actually really struggles because we have a very different length scale in masses. But there are self-force calculation, and then black hole perturbation theory is, I think, something that you will hear much more about in Paolo's talk. Again, this is essentially perturbing a single compact object where you can use analytical techniques, but you also can cover this with numerical relativity. And in fact, for me, this usually is a good benchmark test. Or if you don't have symmetries in your compact object, then you might want to resort to numerical relativity time domain calculations. Yeah, so you need this when you have strong gravitational fields, high velocities, or nonlinear dynamics are important. This is where we want to use numerical relativity. Okay, so how do we go about? And remember, when I say numerical relativity, I'm thinking about the time evolution in 3 spatial dimensions, propagating forward in time. So let's think about how we do that with Einstein's equations that I've written down here. And the first thing that we want to do is actually break this nice covariant form that we have here and make the time dependence explicit. And the first step is to do this for our space-time, where we take our, say, 4-dimensional manifold and split this up into 3-dimensional spatial slices that are labeled by a time parameter. We introduce a metric on each of these slices and have a normal vector onto these slices. And in order to describe, say, the coordinates, we introduce something that's called a lapse function, which tells us how much proper time elapses between these slices, and a shift vector that tells us how coordinates from one slice would propagate to the next. Now, to complement or complete this picture, we also need to introduce something that's called the extrinsic curvature, where we can think about it geometrically as the change in our normal vector as we parallel transport it, say in a curved hypersurface. We can also relate this extrinsic curvature to our spatial metric on each of these slices. So think of this as a kinematic equation where the spatial metric gives us a position and this extrinsic curvature gives us the velocity or momentum of these slices. And this is geometric. So this is something that I would do no matter what model I have. If I want to write down my equations as a time evolution problem, this is typically a construction that I would think about. Okay? And now we have to, in order to get the dynamical equations, we have to apply this kind of 3+1 or space-time decomposition to our dynamical equations. I didn't write those out, but I just want to give you a flavor of what this gives us. So if we take our Einstein's equation, want to write this down as the initial value problem, we would get a set of constraint equations. These are elliptic type partial differential equations, PDE. I'm sorry, I did abbreviate this here, it's written out here. And we typically solve those to get our initial conditions. So if I say I want to start at time t equals 0, I need to prescribe what my metric and the extrinsic curvature is at t equals 0. And some of the degrees of freedoms are determined by these constraint equations. Now, once I have my initial data, I want to propagate this forward in time, and I do this through a set of hyperbolic equations that I get also by decomposing Einstein's equations. And if I do this with Einstein's equations, as I said, I usually get a set of hyperbolic equations. I need to think about how I treat singularities. For example, if I have black holes, what do I do? Because my simulation would, of course, go all haywire if I have a singularity on my grid explicitly. So we have to think about how to treat that. And we have a pretty good understanding on how to do this. The other thing that we need to think about is the structure of my equations, of my time evolution equations themselves. We need to have something that we call mathematically well posed. So if I start with some smooth initial data, then my data at a later time should depend continuously on my initial conditions. Well, why do I care about this as a numerical relativist? That is a very mathematical statement. But in every numerical relativity simulation, I have numerical noise, small perturbations. So I better make sure that these perturbations, this numerical noise, doesn't grow faster than, say, exponentially, because otherwise my numerical simulation becomes unstable, not because of the physics, but because of the mathematical formulation. And that's actually something that the numerical relativity community has suffered from for 30 years before getting numerically stable evolutions. And I think what happened was that there was this very nice proof by Madame Choquet-Broha on the well-posedness of Einstein's equations in a harmonic gauge, in a certain gauge. And then people tried to write the equations in a very different form that turned out to be not well-posed. Okay, so this is something that we need to think about, especially if we want to go beyond Einstein. And I also show this picture here because not only is Madame Choquet-Broha local in Paris, she also turned 100 years late in December. And for me, she is one of the heroes in our field, having proven this in the 50s. Okay, and then the last thing that we need once we have this time evolution formulation is actually thinking about diagnostic tools. How do we extract gravitational waves or other radiation channels? How do we measure properties of our compact objects? So if we have black holes, this would be an apparent horizon finder that we can use as our evolution goes along. If we have stars or other compact objects, we would think about measuring their density, energy fluxes, and so on. And all of this needs to be implemented. And as I said, in general relativity, we know how to do this. Actually, another anniversary coming up. And again, when I wrote the slides and wrote down that the first stable simulations of black hole mergers in 3+1 were done by Franz Pretorius in 2005. So this is another 20-year anniversary coming up now on this. So it's pretty impressive. Okay, good. So let me just go to the next slide. So if, say this is a series, so this is one of the things that we need to think about. And of course, then the next question we need to think about is how do we implement this technically, right? Because now if I write down my metric, extrinsic curvature, all the gauge functions, I end up with 20 plus functions on a three-dimensional spatial grid. And the spatial grid actually has to cover several orders of magnitude. I need to cover the size of my compact objects with sufficiently many points. I need to cover their separation. Typically, that's order 10 of the length scale of my compact object. And then I want to measure, say, gravitational radiation, order a few hundreds of that length scale. So I'm typically, and on a 3-dimensional spatial grid, and that we want to propagate forward in time. So we usually use something that's called adaptive mesh refinement, where we have a very high resolution close to our compact objects, and then use fewer and fewer grid points as we go out, just making sure that we have sufficiently many grid points to resolve our wave. Yeah? That also means that we need to parallelize our codes, and that we typically run our simulations on high-performance computing facilities like this one here, which is an image of the Frontera cluster that we are running on, yes.
So I have a naive question. I mean, the metric, once you fix the gauge, has got 6 functions. Where are the other 14 or so coming from? But most particularly, I'd like to ask, how would this scale as I go up in more dimensions, 5, 6, and 7? How bad is it going to get?
Right. So, you're absolutely right. So in 4 dimensions, we have 6 functions for the metric, for the spatial metric, 6 functions for the extrinsic curvature, and then 4 for the gauge conditions. And we actually write these gauge conditions as evolution equations, so that everything recombines into a nice set of wave equations, because we know how to deal with those. If you go to high dimensions, what I have, so I will come to this. Well, I will mention it. So the way we've dealt with with simulations in high dimensions is to use dimensional reduction to a problem that's effectively 3+1. And what you end up with is a metric, extra scalar fields, and extra gauge fields. Right? So yes, it's increasing the number of degrees of freedom, and this is how we can count them, and it's something that we know how to deal with.
So you know, the physical functions in some sense are only 6 of them. And you get 20. So is that going to propagate, or is it going to be much worse?
So here, so here we are thinking about how we write the system of equations, which I haven't shown you, because the metric, for example, we split up into something that's a conformal factor that has the singularities, and a conformal metric that's regular. And similarly for the extrinsic curvature. So this is how we end up with more grid functions, but then in the end we recombine them to just the base functions.
I guess the question I'm trying to ask is, if you went to 5 or 6, let's just say 5, keep it simple, then obviously when you dimension reduce, you get a vector field and a scale.
That's right.
But isn't it going to be worse than that, because you've got a 5-dimensional grid now and you've got more gauge conditions?
Okay, so what I'm trying to say is that instead of dealing with a, say, 4+1 dimensional grid directly, which I think is still hard and might become numerically expensive, because then you would think about having a box in 4 dimensions that you want to propagate in time. So what you can do if you use either dimensional reduction or really symmetries of the problem, so that you end up with something that is still effectively 3+1 dimensional. So your grid size is still 3 spatial dimensions plus that you evolve in time. So you end up with these extra gauge functions or scalar fields, but it's something that we know how to deal with. So I think it's not as bad as writing a completely new code for n+1 dimensions.
So I guess the comment I'd make is one of the things that's critical to the sort of fuzzball program and things like that is using those extra dimensions to resolve singularities. So it might be important to actually work with 5-dimensional grids or higher dimensional grids.
That might be important, yes. No, I completely agree, and this is something that I think I want to talk with you. How important is it? Or can we deal with the singularities that we get from a dimensional reduction, right? Where I think I do have some ideas of what we could do in practice. Yeah, and I think that... Wait, just a second.
I agree with Nick. When you say dimensional reduction, you mean that the field will not depend on the internal directions?
Yeah, I think that's what I'm thinking.
Because this is crucial for the fastball idea, because in 4 dimensions you will always find singularities and so on.
You do. Yeah, so this is something that I would like to understand better. How much do we have to resolve there, or how much can we approximate it in an effective 3+1 dimensional formulation.
But in principle, you could do directly in 5. Why not?
So it's computationally more expensive. So think about how does this scale, right? So if I say I have n points in one direction, at the moment I deal with n to the power of 3 points because I'm in 3-dimensional space. And a typical simulation size, this is actually a small simulation size where I would run for half a week on 256 processors. More typical high accuracy gravitational wave simulations easily take, a couple of weeks on this. So now imagine you're adding not n to the 3 points, but n to the 4 points, right? So the question is, how do we deal with this in practice?
This is correct, but you can use the symmetries. You can just think of some
That's right.
ideal
That's right.
system which have more
That's right.
symmetries. And then,
That's right. So this is exactly where I say I want to discuss with you how can we write this down as an effective system without having to write a 4+1 code or 5+1 code, because you also want to have a formalism that is adaptable to different high dimensions, and then in this way more flexible. Yeah.
Just a quick comment. There might be good singularities in 3+1 and bad ones, and we may be able to have to think about that.
Yeah. So this is something I really want to learn. Also, talking with you this week. I think Roberto has a question. I don't know where the ball, the cube is.
I mean, I think that, correct me if I'm wrong, but I think that the fastballs that you're aiming for are spatial cohomogeneity 4. Instead of talking about dimensionality, I'm talking about cohomogeneity. And spatial cohomogeneity 4, that's something that's beyond the capabilities of current numerical relativity, right?
So
that would be total dimensionality, space-time cohomogeneity, that would be 5. Space-time. Well, of course, you can always go to, impose symmetries and then you reduce. But every time that you reduce, you're losing.
Right. So you're thinking you need really something where you're in 4+1.
That's what you guys. But I think that's my understanding,
so
right?
Joseph, use the microphone.
Yeah.
I think PR solutions are space-time cohomogeneity 2, and when you smash 2 of them, you'll get cohomogeneity 3 problem. So that's a 4D doable problem.
Yeah.
I think with that one.
Exactly.
Now there are more complicated ones, of course.
But the comment I'd also make is that there are things that are only effectively dimension 2 or 3 that are really interesting.
Yes.
But the space-time being 5 or 6 dimensional is critical to those regularity.
That's right. But this is a different. Sorry. Yes. Go ahead.
Yeah, but that's just to say that, you can only go down in dimensions so much before you lose completely the fastball picture, right?
That's right. So all I'm saying is that I think there might be interesting problems if you use some symmetry. So not going to spherical symmetry or axis symmetry, but still in 3+1, even if your space-time is high dimensional and you reduce to 3+1, I think there are interesting problems that can be addressed. And that also gives us time to understand how to deal with those equations before starting to write, high-dimensional code explicitly, so if that makes sense. Good. Any other questions about this or comments? Because otherwise I will continue. If you want to hold on to this. Oh. Okay. Good. So the last thing I wanted to say here, of course, the techniques that I was describing, their main application was for gravitational wave modeling in general relativity, and people have done this. So there are, now catalogs of more than 5,000 simulations covering a wide range of parameter space for masses and spins of black holes. But really, what I wanted to give you an idea of is how we can go beyond general relativity and beyond the standard model. So this is now the next part, thinking about numerical relativity for fundamental physics. And the first thing that I wanted to give you is a bit of a list of what people have thought about and why I think that we are ready to start extending these methods to think about microstate geometries. Right, so if I think about microstate geometries that are smooth horizonless solutions to supergravity that may have or should have the same charges as masses and potentially spin as black holes. But how do I describe that? If I say supergravity with these charges, I should have as field content a metric, I should have complex scalar fields, I should have gauge fields, and I may have to deal with high dimensions. And I know this is very reduced, but trying to get the essence of what is it that we need. Now let me give you a list of things that people have thought about in numerical relativity, and don't need you to read all of the details, but people have thought about adding extra fields. From just thinking about modifications to general relativity that are scalar tensor series, the vanilla type 1 and Hondesky gravity, people have thought about boson stars, people have thought about adding very light scalar or vector fields. And I have done work in especially these latter two. Then maybe a little bit outside of what's really needed for microstate geometries, but people have thought about higher curvature corrections. Aaron Held is here, who has thought about effective field series of gravity. In my group, we've been thinking about quadratic gravity, namely scalar Gauss-Bonnet gravity and dynamic Simons gravity, and I think I will show you a couple of examples here. If you don't believe in them, that's fine, but there are a few lessons learned in terms of how can I write those equations that I would like to share with you. And we had this discussion just now, but there has been work on simulating black holes in higher space-time dimensions. Actually, during my PhD, I was writing a code doing exactly this dimensional reduction approach to look at collisions of black holes in 5 dimensions. So this is why I have an idea on how I can deal with some of these singularities that arise when you do this dimensional reduction. And there has been very nice work thinking about the stability of black holes in higher dimensions, where you have a much richer solution space. I'm not going to go into any of the details on the high dimensional gravity part, but I'm happy to talk about this over coffee or dinner in more detail. Good, so the first example that I wanted to share with you is about simulating black holes coupled to very light scalar fields. So here, I actually will show you this in a moment. I also wanted to say that I think for today I will focus on work done in my group, so I wanted to give a shout out to my group back in Illinois, which by now actually counts 10 people, including graduate students, postdocs, and visiting research scholars. And I do want to focus on the code that we are using, so I do want to advertise the open source numerical relativity code that we are developing in our group, and then I will talk about black holes coupled to light scalar fields, and think about black holes in modified gravity as well. So the code that we are using, it's not the only one, but it's something that I've been co-PI of for many years, and sorry, I do run in front of the slides here. So the code that I've been co-PI of is the Einstein Toolkit. It's an open source numerical relativity code for computational astrophysics. So if you're interested in doing simulations in general relativity, you can go to our website, download the code, install the code, and run it. And there are a lot of tutorials on how to use it. We have a school every year, one in the US, one in Europe, if you want to learn how to do it. And we usually have those in hybrid mode and record our lectures. Now, if I'm interested in applications in fundamental physics, I actually wrote my own code in collaboration with Miguel Ziliao. Also Alexandro Dima, who's in the room here, Hector Ocada Silva has contributed, where we are really writing our own code modules to answer questions in beyond the standard model, from adding extra fields to modified gravity. And our code, again, is open source. It's called Canuda. Ask me about where the name comes from afterward. So it's open source code for fundamental physics, and it's actually also being used by groups outside our own, like the group in Valencia has used our implementation to look at boson star collisions. Okay, so this is the code that we have. It's not the only one, but I want to advertise it because it's open source and it's something that we are developing. So any new implementations, any new modules that I'm developing in my group will be open source and accessible to everyone who's interested in doing science with it. Okay, and now, sorry, there we go. And now I will tell you about the application with black holes and very light fields. The physics motivation here is that we can think of these very light scalar fields as candidates for wave-like, very light dark matter. For us, it was also a proof of principle problem to consistently solve Einstein's equations together with the Klein-Gordon equation. So complex or real scalar fields. Implementation is for complex scalar field. We can switch between complex and real as we need it. One of the physics motivation was to think about how we can use black holes to probe for very light beyond standard model particles. But we also realized it's actually a good toy model to think about how an environment might affect our binary black hole coalescence. And as I said, we are solving this consistently. And what we have here, what I will show you first, you have a question, Roberta? No, okay. So what I want to show you first is actually the evolution of the scalar field in the XY plane. Maybe something to note is that I use geometric units. So speed of light equals to 1, Newton's constant equals to 1, which means I measure distances and time in mass of my total object. Okay, so hence x in units of total mass m. And what we have here is a spherically symmetric Gaussian scalar field surrounding a binary black hole that's hidden beneath it. And I think I have to click here to let it go. So what you will see now is as our scalar field starts evolving, it actually starts being accreted around each of our black holes. So it's almost like we have two black holes with a scalar charge in quotation mark, that is orbiting around each other. And these two orbiting scalar charges are generating scalar radiation. In this case, we have a black hole with a mass ratio of 1 to 2, so the scalar radiation is a dipole and carries energy away from our binary. Now, by this argument, you could say, well, if my scalar radiation carries energy away, this should accelerate my in-spiral, and my black holes should merge earlier, which should be reflected in a gravitational wave phase shift with a peak being earlier than what I have in the vacuum case. Now, this is contrasted with the possibility that our black holes are also dragged by the scalar field. So maybe slowed down by the scalar field and therefore slowing down our coalescence. Well, why do I tell you both of this? Because now we've done a series of simulations where we varied the mass parameter of our scalar field between 0 and 1. And what I'm showing you here on the left, and I know it's a very busy plot, on the left I'm showing you the gravitational radiation measured by the Newman-Penrose scalar as a function of time, and again measured in units of m. And the different colors correspond to different values of our scalar mass parameter between, as I said, 0 and 1. It's hard to see here, but it seems that there is some kind of shift with respect to the vacuum before and after. Since it's so hard to see, we actually computed the shift of the gravitational wave phase, again as a function of time. And you can see here that there are a few cases for very high masses where we have a positive phase shift corresponding to a later merger. So I think this is where we have some dragging, whereas for small mass parameters, we have a negative phase shift, so an earlier merger where I think the scalar radiation is very efficient. Good. So this is actually work in progress. We're writing this up with my current PhD student, Cheng-Ching Cheng, and former student, Giuseppe Ficara. And this is where we stand right now. Okay, so Nick, how am I doing in time?
10 minutes before.
10 minutes before,
So
okay.
5 minutes of more talk and
Okay. So in that case, let me think about, so I do want to show you a little bit about the lessons that we've learned from thinking about high derivative gravity. where you can derive the Lagrangian that I wrote down here actually from heterotic string theory, taking a low energy limit and doing a dimensional reduction to 4 dimensions. And what you end up with is, our beloved Einstein-Hilbert term here. You get a dilaton field that I labeled phi. You can have this dilaton field coupled to the Gauss-Bonnet invariant, which is a Riemann squared type correction. And if you don't restrict yourself to even parity, you also get an axion field. I label this as theta, and this would be coupled to the Pontryagin density, and this is called dynamical Schoen-Simons gravity in the gravity community. So this is one of the things that you can get. And if you have this action, one of the things that you will get is black holes that now carry dilaton or axion here. Well, before I show you one example of a simulation, and I think that this is all I'm showing you for this, I want to tell you about some of the lessons that we've learned by looking at these problems. Because if you write down the equations of motion for what I call here scalar Gauss-Bonnet gravity or dynamical Schoen-Simons gravity, what you get are equations of motion that are second derivatives of the metric but to higher order. So this is what you get for scalar Gauss-Bonnet gravity. So highly nonlinear equations of motion that can actually be elliptic and hyperbolic depending on where you are in your space-time. So how do you deal with that? Right? Dynamical Schoen-Simons gravity is even worse because that gives you third time derivatives of the metric. And we actually don't have a very good treatment of that one yet. So there are overall 3 main approaches of what people are doing to make the equations of motion well posed. As I said, we need that as a necessary condition for numerical stability. So the first and maybe simplest approach that you can think about is an order by order expansion, where you say, oh, let me expand my metric and my extra fields in around general relativity, and let me take my coupling parameter as my expansion parameter. What you get at each order in this expansion is essentially my Einstein tense operator acting on the field at that order and source terms from lower orders. So this is nice and easy to implement. It's actually nice for stationary solutions, but as soon as you have a binary problem, you get circular effects that are non-physical and just an artifact of this expansion. So not ideal. It tells you something, but it's actually not great to use. Then another approach, and I can go into details afterwards, is to try and regularize the equations in the same way as this is done in relativistic hydrodynamics, where people use a trick that's called Israel-Stewart, where we basically introduce auxiliary variables and an ad hoc evolution equation that drives them to the solutions that they should be. And this is what people do, as I said, for relativistic Navier-Stokes equations, which are ill-posed. And then there's very nice work by Aaron Kovacs and Harvey Real, where they introduced a modified gauge condition, and actually, at least for scalar Gauss-Bonnet gravity, for sufficiently small couplings, this gives stable evolutions, and people are now solving this in full. So this is something that we can use. Okay, so I think I will skip this. I think I will only talk about the one example for true binary black holes in scalar Gauss-Bonnet gravity, but in this decoupling approach. I just said it's bad, so I'm only showing you the scalar evolution. And this is work that I've been doing with Paolo and collaborators back in 2019, where we had a binary black hole in the background described by general relativity, and we were looking at the evolution of the scalar field determined by this equation here. And again, what you get is black holes that now really have scalar hair. So what we're seeing here on the left is amplitude of the scalar field and in the equatorial plane. And these bulges or maxima here indicate the scalar charge, larger scalar charge around the smaller mass, higher curvature black hole. And let me try to make this go. Here we go. Yeah. So now we see these two scalar charges that are dragged along with our binary black holes in the background, orbiting around each other and slowly generating scalar dipole radiation. And as I described before, since we now have the scalar dipole radiation that carries energy away from our system, if it were to back react, it actually accelerates our in spiral and leads to a gravitational wave phase shift in the end. So I will just finish with this simulation, and I think then I want to go to the conclusion and basically pose some of the questions. Okay. Yeah? Okay, so, and yeah, so there are a few more precise computations that people have already done, but yeah, so the question is, can we use numerical relativity for microstate geometries? There's one proof of principle calculation by Paolo. Are you going to talk about this? And no hurry? Okay, well then I will advertise Paolo's work. Then I will advertise Paolo's work. So I don't know, are you going to talk about this in detail? Just a few words. Okay, so then I do want to advertise this because what Paolo and his collaborators have done is actually first proof of what I would call a proof of principle calculation, considering a specific a set of specific fastball geometries. And what they were looking at is the evolution of a test scalar field in that fastball geometry. So think about having your background, your geometry fixed. In this case, the one that I'm showing you here is a fastball with 3 centers. And as I said, evolving the scalar field on top of this. Because you now have fewer symmetries, you actually do need to solve this problem in at least 3+1. And again, doing this in perturbation theory is really hard, but we know how to do this in numerical relativity, and this is what they did. So they evolved this test scalar field around this geometry. And one of the plots that I took from their paper is now the L equal 2, m equals 0 multipole of the scalar field as a function of time, and again everything measured in units of mass of our space-time. And what you see here is initially a ring down, but then followed by the subsequent what people call echoes. And this is something that could be considered a smoking gun effect as something that's not just a Kerr black hole, but we might have these very specific echoes here. So this is, as far as I could tell, the only numerical relativity simulation of microstate geometry. So it's really starting to go into this direction. So with that, I do want to summarize and pose some questions and discussion. So I hope I could convince you that there are, first of all, plenty of gravitational wave observations of the gravitational universe, and there are more to come. So it's really an exciting era to be in this field, to be able to probe fundamental physics with gravitational wave observations. In order to do so, we do need to model what our gravitational wave signals or other observational signals would look like if we don't have our beloved black holes in general relativity. Yeah, how does our signal change? And this is very much in the spirit of what you heard in the first talk, but now applied to gravitational waves. I also told you that numerical relativity is a tool that's very well established to model the non-linear dynamical regime of gravity, and we have different puzzle pieces. We know how to do scalar fields, we know how to do gauge fields coupled to gravity, we know how to do some higher derivative gravity models, we know how to do some high-dimensional simulations. So what I want to argue is that we can actually address some of the open questions in the microstate geometry program, such as new dynamical solutions, nonlinear and linear stability, and if there's instability, the new end state with numerical relativity. And I think we have all the puzzle pieces that we need to do this. So of course it's not going to be super straight, so it's not going to be easy, but I think we know what we need to do. So it's something that we can do on a few-year timescale. What we do need to think about, and this is something that I just copied over from an earlier slide, of course, is to think about what are our constraint equations, initial conditions? What is the time evolution formulation? What is the gauge and treatment of singularities, and how can we diagnose? But I think it's something that is within reach, and this is what I want you to take away from this. So thank you.
So questions, I think.
Thanks. I have two questions. So can you maybe say something about singularity? So for example, in the scalar waves from Paulo and company, this is a scalar on a fixed background, and so essentially, you kind of ignore or smooth out what happens around the singularity. So what would you do if it becomes dynamical? Because those singularities are really crucial, right? They're the structure, as it were, of the fuzzball. So how can you treat them numerically? Can you deal with them?
So what I'm thinking, and this is exactly one of the things that I want to discuss, because you're absolutely right. What I think, Paulo, what you folks did was regularize the singularities. So one of the lessons that we've learned when we did the simulations in high dimensions, doing the dimensional reduction, where you did get an extra field that was like the radial coordinate in the extra dimension. So yes, as that goes to 0, there is a singularity, but we could regularize this as well and do dynamical simulations of the metric. And I'm thinking if singularities are of this type, we know how to deal with it.
So you essentially you regularize so this is like the size of the extra dimension. You just say like, okay, there's some minimum size.
So if that goes to a size 0, then we can regularize it. Or if it's a radial coordinate, we know how to deal with that radial coordinate going to 0.
Radial as in the size of the of the circle. Okay.
Yeah.
And then I guess you have to there's problems of like when you make the usually you have multiple centers that go singular, and then you want to put them close to each other, and then
so one of the things would be is to think about how can we regularize this in a dynamical evolution, right? And then the next question, if we start with a single object, I think we probably have this localized in space, so it's probably easier to deal with than thinking about what we would do in a like binary system.
Can I ask another question?
So does anybody else going to have anybody else want a quick turn? Okay, go for it.
It's maybe a shorter question. I was just wondering, because I know a lot of scalars that are simulated typically have just a standard kinetic term, and so one of the big things, of course, also in fuzzball supergravity theories is you have some really weird, scalar dependent kinetic term. Does that screw up the well-posedness of the scalar guys, or?
We would have to look at the exact form of this. One of the things that people have done is, add a scalar field potential. Actually, the example I showed you was just adding a mass potential. This is straightforward and easy to do. There are models of Hondesky gravity. If you don't know what Hondesky gravity is, it's the most general scalar tensor theory of gravity. So it can have in your action higher derivative terms, but in the end you still have second derivatives to some power in your equations of motion. So people are, by now know how to deal with this.
Sorry, I meant like the d phi squared is not just d phi squared, but there's some function of phi in front of that.
Yeah, but you know how to deal with that.
Okay.
Yeah.
Any other questions? Okay.
So did you have to assume anything on the coupling, whether it should be weak or strong, or it's for the Gauss-Bonnet? Scalar Gauss-Bonnet. So
the example that I showed you is that the coupling function is linear. We also know how to deal with it when it's exponential. The example that I didn't show you was thinking about a quadratic coupling that gives actually new non-linear effects in the evolution. But so we kind of have different couplings there, and then for the coupling function, if you the coupling constant in front of it. Here I was working in the decoupling limit, so I scaled this out. But if you do the full simulation with this modified gauge conditions, you need to assume this coupling to be sufficiently small.
Okay. I have a brief question. When you go to higher dimensions, you open up a whole new Pandora's box of possible instabilities. The obvious one is Gregory Laflamme, but there are other things that we find in fuzzballs and microstate geometries. For example, some of them have this extremely long-term trapping near Evanescent-Ergo surfaces, which have been argued but refuted that these are significant possible places where you could develop singularities. Isn't that the place where the numerical code is going to start screaming, or is this going to be okay?
So what kind of instability is this?
Well, okay, let's start with Gregory Farm is the obvious one, but
Yeah.
if you have an ultra-compact object with extremely long-term trapping, stuff will build up there, and then... you know.
Right. So I guess I would be concerned more about the timescales, because for me instabilities are interesting if they are physical, and granular flamme is something that people have simulated on the computer, right? So I think I get worried if I understand better what is the build-up, how does this look like, or is this something that is interesting, and is this something that, if we include back reaction, can actually give rise to a new stationary state. So I think in that sense, for me, instabilities are always interesting because they give rise to new types of solutions. Yeah. Yeah. Oh,
Any other questions? Okay, well, let's thank Helvi again.
thank you.